So when we get into chapter 9, what we're going to start looking at is different types of series. We're kind of looking at how you can approximate a function with polynomials. So we start by looking at what we call a power series. Okay, so first of all, I see that I had some mistakes on this. Okay, this thing that says I equals 0 should say n equals 0. I obviously typed that wrong. Okay, so these are all examples of power series. Now what's different about this is every series you've seen so far hasn't had a variable x in it. It's had like a variable k or a variable n. Okay, typically k is what you've seen most often. So power series, now we're talking about variables. So what I want to do on this is just kind of write out some of the terms of this to kind of show you what a power series is. So first of all, when we say centered at an origin, now a power series has this type of structure. It's going to have, if it's centered at the origin, we say like x minus 0, okay? And then you might have like a x minus 0 squared, x minus 0 cubed, and so forth, like that, okay? So that would be kind of a structure of a power series right there, and you might have a constant. Typically, you might have even like an x to the 0, which would be a constant term like that. So that's what power series are, is they're powers of x, okay? So let's write some terms out on some of these things to begin with. So let's see, let's say with this one, let's start with 0. So if we did this, we'd have a sub 0 times x of 0. I'm just going to have you write out some of the terms. Then we go to the next one. Of course, n would go to 1, so we'd say a sub 1, x of 1. Then we would say a sub 2, x of 3, and then so forth. Well, not 3. Okay, tell how early in the morning it is. I think 2 comes after 3. Okay, so that's a to the x to the second. Then let's do one more. We'll say a sub 3, x to the third. Then it just goes on and on forever. And a sub n, x sub n, like that. So that's kind of a typical power series. If I say centered at the origin, that just means you have x minus 0. So you don't really have, you just have powers of x, okay? All right. If you're centered at a constant c, it just means you might have something like this. You might have like x minus pi, you know, something like that to the first, and x minus pi to the second, and so forth like that. So that's the idea. So power series, we're talking about powers of a variable x. So let's write out the terms on this one. Think again, this one is supposed to say n equals 0 instead of I equals 0. So let's see. First term, we'd say a sub 0, which is just some constant, times x minus c to the 0. And then we would have a sub 1, x minus c to the first. Then we'd have a sub 2, x minus c to the second, and so forth like that, just to kind of get the pattern. All right. So that's what power series look like. Does that make sense to everybody? All it is powers of x, and these things are basically look a whole lot like a polynomial function. That's what they really are, is you have integer powers of x. That's what polynomial functions are, and you have sums, okay? Here's 2 examples of power series. So we're going to just write out the terms on this before we start doing anything with power series. So let's see, again, that's supposed to say n equals 0. Okay, so let's just kind of look at the first couple of terms here. So if you're doing n is 0, you'd have negative 1 to the 0, and then you'd have x to the 0 over 0 factorial. Okay, so that would be, the whole numerator would just be 1 times 1. What is 0 factorial? Yeah, that's by definition. Okay, we have to define that 0 factorial and 1 factorial are 1. Okay, that's a mathematical definition. So anyway, your first term would just be 1. Okay, and let's crunch out the next one. Usually after you get about 2 terms in the series, you begin to see the pattern. So let's go to negative 1 to the first, x to the first over 1 factorial. So now, what kind of number are you going to have, negative or positive? Negative, okay, so you're going to have an alternating series. 1 factorial is 1. So this is going to just give minus x to the first or just x like that. Okay? And then let's do one more term. Let's go negative 1 to the second, x to the second over 2 factorial. Okay, well, that's an even exponent, so that's 1x to the second. 2 factorial is 2 times 1 or 2, so that's going to give plus 1/2 x to the second like that. Okay? Now, if you, by the same argument, if you went to the next one, if you did, I'm going to do one more term, negative 1 to the third, x to the third over 3 factorial, that's going to be negative 1x to the third. 3 factorial is 3 times 2 or 6, so now you're going to have a minus 1/6 x to the third like that. Okay? So that's how you would write out the terms of the series like that. Okay, does that make sense, what I'm doing to everybody? Okay? Okay, we've done a lot of that. You've written lots of terms of series out. So, and again, notice what this is. This is a polynomial. That would be like some function that you would have learned something about in college algebra. Okay, so power series can be written as a polynomial. Okay, so this thing right here, since it's just x to the n, that would say that that is centered at 0. So that's the idea. Okay, then let's do one more. Let's write out the terms of just one more of these things then like this. You don't have to write down all this number crunching I'm doing over here. You just need to understand how that's all working out. And I'm going to do that just on a couple of terms on this one. Okay, again, this one's supposed to say n equals 0. So if you started with n equals 0, you'd have negative 1 to the 0, x minus pi over 4. If you plug in 0 there, that would be 2 times 0 plus 1. And then the denominator would be 2 times 0 plus 1 factorial. So let's see, that looks like that's, of course, going to go to 1. That's going to be x minus pi over 4 to the first. And that looks like that's 1 factorial. Okay, so what is that term? That's just 1 factorial is 1. So that first term is just going to be x minus pi over 4 to the first. You don't have to write that first on there, though, obviously. Okay? All right, does that make sense? How that's crunching out? Okay, let's do one more, and then I'll just have you write out, one more term on this. So let's go to n equals 2. So then you would have negative 1 to the, or n equals 1. Negative 1 to the first. Then you would have x minus pi over 4 to the 2 times 1 plus 1. And then that would be 2 times 1 plus 1 factorial, like that. Okay, so what kind of answer do you get, negative or positive? Okay, you guys see the alternating series in there, right? Okay, that's that negative 1 to the n, of course, is what causes that. So you want to recognize that immediately. So that's negative, and then this would be x minus pi over 4 to the third power. Okay, and then the bottom is going to be 3 factorial, which is 6, 3 times 2. So this is going to give minus 1/6. Okay, like that. And then this term is going to be x minus pi over 4 to the third like that. Okay, and that's how that would go. All right, then the next term in the series, I'm just going to write the next term. It's an alternating series, going to go to plus. You're going to end up with a 5 factorial. And let's see, 5 factorial is 5 times 4, I think it's 120, if I remember right. Yeah, that's 120. So that'd be plus 120. And then this would be x minus pi over 4 to the 5th power like that, and then it would continue. Okay? So do you guys know what 2n plus 1 represents, by the way? That's important. That's an odd number. Okay? That's worth writing down. We've seen that before. So if you have 2n, that's an even number, and then anytime you add 1 to an even number, you always get an odd. So when I look at that right there, that's telling me that I have odd integers. So these exponents are going up by odd powers, 1, 3, 5, and so forth like that. And these factorials are going 1 factorial, 3 factorial, 5 factorial, and so forth like that. Okay? So what I wanted to show you on the first page primarily is some examples of power series, what they look like. What's different is we now have an x in our power series. We haven't seen that yet. Our series have just had n's or k's in it, and that's it. Okay? All right, is there any questions so far? Let me ask you one other question. What would this one be centered at?
Pi over 4.
pi over 4, right, okay? So remember, if you're centered at something, it's x minus something to the n power. So pi over 4 would be what we call the center, okay, like that. So as we go through this section, you'll hear me talk a lot about the series being centered at something. Okay, any questions about anything so far? Okay, all right, so basically what you're kind of looking at is these things are looking a whole lot like polynomials, okay? Polynomial functions basically are just sums and differences of powers of x, whole number powers of x. So a power series is basically creating some sort of a polynomial, okay? All right? And we call this a super polynomial, hence the Superman symbol, okay? All right. So let's move on to the second page. And what I'm going to do on this is something that you generally do a little bit of in Calc 1. So we extend on this idea a little bit in Calc 2. So we're going to look at like a linear approximation. So first of all, the thing I want to mention on this is when you study polynomials like in college algebra, basically what you have is that you have these operations. The operations are arithmetic. You have addition. You're subtracting. Usually you have plus or minus signs separating the terms of the polynomial. You have multiplication. You have a division in there, usually maybe with a fraction. You have exponents and that kind of thing. So what we're going to work with is I'm going to do a review of linear approximation. So what we do is when we're doing like a trig or a logarithmic exponential functions, we can approximate those by polynomials. So one of the things you're going to see is you could take something like a natural logarithm and you could write that as an infinite series of a power series. We call that a Taylor polynomial, which we'll introduce that idea today. So let's draw a little picture on this. I think I gave you a kind of a blank graph. So let's do something kind of like this, because I want to see if you guys remember much about this from Calc 1. We just barely introduced the idea here. So the idea would be if you have some value, I'm just going to call that some generic value like x naught, and you wanted to use that to approximate another value on the function. So I'm going to go to another value on the function that's a little bit to the right, and I'll call that x, okay, like that. Well, what you're going to have is, of course, this value right here would be the function value. So that's f of x naught like that, okay? Now what I want to do on this is I want to do a derivative at that x naught like that. So what I'm going to have you do, I'll try to draw this fairly accurately so you can get a good idea here. We want to draw a tangent line kind of through that point, kind of like that, okay? And then what we're going to do on this is this term right here, I want you to do one other little thing here. Just write that over like that as f of x like this, okay? So you may remember this from Calc 1. You learned something that's called linear approximation. This is where you use a derivative to approximate a function value. So the idea is f of x and the value of this derivative. See, this is a value right there of that derivative. That would be f prime of x right there. They're relatively close to each other. They're off a little bit, but they're fairly close to each other. Do you agree with me on that? Okay. So the idea is, and then this is really f prime of x, and then this right here would be f prime of x naught. So you're tangent at that line like that. Okay, so what we do is we say that f prime of x approximates the function like that. Does that make sense? That the value on that derivative would be fairly close to the value on the function. You know, assuming that x1 and x are pretty close to each other. Obviously, the further out x goes, depending on how the function behaves, you might have a little bit different error there. Okay, does that make sense to everybody? Okay, all right. So the idea is is going to be, we're going to do a linear approximation. Now, I'm going to go ahead and just do an example, and then we'll kind of review the formula that you would have learned in Calc 1. So what we're going to do is we're going to develop the formula. We're going to approximate what the square root of 26 is using this idea right here. Okay, so to begin with, what we're going to do here is, since we're doing a square root, we're going to work with the square root of x. And let's see, I'm going to go ahead on this, and I want to just have you label things kind of like this. Let's go out somewhere on the x-axis, and I'm going to go to 25. The reason is, the square root of 25 you know, correct? Square root of 25 is 5, and that's a number that we know the square root of that's close to 26. Okay, then I'm going to put like the 26 out here. Now all I'm going to do is just have you roughly sketch the square root function. You probably remember square root function looks like this, kind of does a swoosh, right? So let's go make the y-axis go up to 5, because we know the square root of 25 is 5, okay? And then I'm going to go ahead and have you, we have the point square root of 25, 5, and then just kind of approximate that like that. That's kind of what your square root function looks like that, and then label that f of x equals square root of x, okay? All right, now what I'm going to do is I'm going to show you how we can use a derivative to approximate the value of the square root of 26, okay? So the first thing that you want to do on this, basically, is we want to use, we want to go ahead and do the first derivative, okay? So let's see, square root of x we can write as x to the 1/2. You want to go ahead and just do the first derivative of this, and then hopefully this example will help you see kind of what's going on with linear approximation. So that derivative is 1/2 x to the negative 1/2, and then let's go ahead and write that as 1/2 times square root of x. Okay, so we're going to do that derivative to begin with. Okay, so here's what we're basically going to do on this. So the other thing I'd like you to do is, let's go down like that, just kind of continue drawing this diagram like that. So I'm going to call this, generally we call that x naught, okay? That's what we're comparing this to, and of course this is f of x naught, which of course is 5, okay? And then we're going to do the derivative, we're going to go out and draw the derivative, the slope of the tangent line like this. So what I want you to do next is just sort of sketch a tangent line that kind of goes through. Doesn't have to be perfect, but something kind of like that. Let's label that f prime of x naught, okay? Or f prime of x, not x naught, just the general derivative like that. Okay, so here's kind of what happens on this is, what we're going to do to get an approximate value. So when we approximate the square root of 26, what we're going to do is we're going to do these two things. We're going to do f of x naught, okay, which is the square root of 25, and then we're going to add to that basically the derivative f prime of x naught also like that. Okay, that's what we're going to do. And then this will kind of help you, I think, see kind of where we're going with this. Okay, x naught is f of 25. The reason I'm using 25 is because I know it's square root, right? Okay, now let's go ahead and find what f prime of 25 is then. All right, so let's do that next. I'll do that at the side. F prime of 25 is going to be 1/2 times square root of 25. So again, I'm just plugging in that 25 into that derivative. Okay, so if we do that, it looks like we get 1/2 times 5, or 1/10. Okay, now what that represents is, when we go ahead and work this out then, f of 25, what's f of 25? Well, that's 5. That's doing the square root of 25, right? So that's doing square root of 25, whereas this was doing 1/2 times square root of 25. That's evaluating derivative. So what we get is we get 5 plus 1/10. So that means an approximate value, just using the first derivative, is going to be about 5 1/10, which is about 5.1. Okay? Now let's see on a calculator. Let me pull my calculator up here real quick. And just see if see what maybe the first decimal is. Okay? So this is only an approximation of what that value is. Okay, so let me pull this up here. Oh, come on. Then there's a couple other things I want to show you on the diagram to see if this makes sense to you. So if I go square root of 26, then notice I get about 5.1. Okay, 5.09. This is a more precise answer, obviously, because actually the calculator is doing something that has to do with a series in the background. So that would be the idea. Okay, now one other thing that's probably real helpful to you is, since this is the slope, that's the slope of a line, what's really going on in this problem is from this point to this point, what we really did is we went up one, and we went to the right. Hold on, that's not right. That is 0.1. So what I'm doing really is this. Okay, this is what I want to show you here. So if you do a decimal for 1/10, that is 0.1. If I put that over 1, that means that your rise is 0.1, while your run, you're going to the right, is 1, like that. So what I'm wanting to kind of make sense, hopefully this helps you make sense of this, is since that value of that derivative is 1/10, what we're doing from the 25 is we're going up 0.1, right 1 to get that function value of 5.1. Does that make any sense? Okay, that's called a linear approximation. Did you guys do some of this in Calc 1, just at least a tad, a touch? Okay, so that's a pretty good example to show you how you can use a derivative to approximate a function then. All right, does that make sense to everybody? Is there any question anybody's got about that so far? Okay, all right, let's go to the next page. And I'm going to give you this linear approximation formula, and we'll talk a little bit about how you derive this. This is what you learned in Calc 1, is this linear approximation formula. The L of x stands for the linear approximation. Okay, so let me do just kind of a quick little derivation here. So let's do, on this, let's draw just kind of a generic function of some sort. Let's say that that's your function f of x. Say that you have something kind of like that. Okay, and then let's label kind of the key things here. Let's say we have a point going down like that, and I'm going to call that x naught. Generally, we're going to let that be just some constant like a. A is what they're going to use in the linear approximation formula and the definition down there. Okay, so of course this over here, you want to draw that over and label that as f of x naught, or f of a if you prefer. And see, that's going to be showing up in this formula right here. Okay, then what we do on a linear approximation, just like we did on the previous example, we go out a little bit to another number that we're approximating. So now we're looking at L of x. We're approximating the function value there using the derivative. So we go up here, and then you would kind of move over to the function like this, and then that would be f of x like that. Okay? And what you're doing with this, again, in general, is you're doing a tangent line like this. That may not be totally accurate, but it's probably good enough. Okay, like that. So that's going to be f prime of x. Okay, and what we're going to be looking at, really, we're looking at f prime of a. Okay, so I'm just saying this is the value that we're interested in that's going to help us approximate the function value at something over to the right, like that. Okay. Well, what happens is on this is you're going up a slope right like this. So what you do with this, let me show you kind of where this formula comes from. So we know the slope is equal to the rise over the run. And I'm going to try to use the previous example I did to kind of help you see the derivation of this formula. So what I'm going to do on this is I'm going to solve this equation for the rise. So I'm going to multiply both sides by whatever the run is. So in general, I'm going to get the rise is equal to the run times the slope, kind of like that. Okay, and then what we do is our approximation formula ends up going like this. Okay, so just like we did, remember we're approximating this value right here. Well, what we did in the previous example is we did this. We did f of x naught. Okay, remember that was like the square root of 25 in the previous example. Okay, then what we did on that is we basically just added on the slope on that is what we did. So we ended up doing that. So I'm going to put on there the slope. And what we did really is we just sort of added that rise over run like that. So what we do is we're going to go ahead and just add on that rise. And if you think about that, see what we're doing is that rise is going to be what the value is on that derivative. Does that make sense? I mean, all we're doing is we're just going up whatever the rise of that slope is to approximate that value. Okay, but the rise can be written as this, the run times the slope. So you would get about f of x like this, and that would be f of x naught right there. And then the rise is the run times the slope. Okay, so what we'd end up having here is, and I'm going to go ahead and just call x naught a now, so it kind of matches the formula that I have down here. And then the run is going to just be this derivative right here. This is the run right there. So that's your run. That right there is your rise, like that. So when we do the run, okay, that's just going to be the difference between these values. So what's the difference between x and a? Well, you just subtract those two. So you get x minus a. That's what the run is. Okay, and then the slope, well, that's the derivative. So that's your first derivative. So you get f prime of a like that. Okay, that's a derivation of what we call the linear approximating formula. Now, the other thing I want to show you on this is really this formula, when you get right down to it, let me show this to you, is if you have, you probably remember this formula from this class and all the way back to college algebra or even intermediate algebra. You have y minus y1 equals m times x minus x1. You know, the linear approximation formula is really this formula. In reality, it really is, because that slope is just the derivative. This thing right here is the linear approximation. And then this thing right here is f of a. And then the x minus a is this part right here. It's the same thing. Does that make any sense? Okay, now I want to give you some sort of a background for where this comes from. But, you know, we're going to be working with this formula and extending this onto what we call quadratic and cubic approximations in calculus, but that's the idea. So when I look at this, I just think of it this way. This is how I remember this formula. This is y, that's y1. That's the slope, so that's the derivative, and that's this. So like if you move that y1 over there, don't you get exactly the same formula? You guys see what I mean? Those are the same, that's the same, that's the same. That's what it is. Okay, now that's a derivation of that, just saying add on the rise, so just take whatever that function value is, plus the rise gives you an approximation. Those two values right there are fairly close. Okay, does that make any sense? I have no clue when I look at you this morning, okay? All right, so I think usually students see this connection, and if you see that, that's good. Okay, so what we're going to do with this is kind of extend this now. Now, I'm not going to do a proof of this. If I had a little bit more time, I would give you this term right here, but the idea is the examples that I did before were stuff you learned in Calc 1. Since we're learning about series now, then you can extend this. So I want to just sort of talk about what quadratic approximation does, okay, and the idea. So first of all, whenever we have this, usually if you have like P1, that's called, we use that to represent the linear approximation. If you go to P2, we call that quadratic, P3 cubic, and so forth. Once we get to P4, that's usually a fourth degree polynomial or a quartic, and beyond like that, okay? So here's kind of what I want you to see is the formula. We're going to learn how the formula works on this. I'm not going to prove this though. So P2, that's the quadratic approximation, and what it has is it has the linear approximation right there. So what I want you to kind of make a note of is that right there is the linear approximating formula that we talked about and what you talked about in calculus. And then this piece right here is going on to the quadratic approximation like that. Okay, now what happens on this, and this is going to have a real nice kind of structure to it. When you go on to that quadratic piece, you have the second derivative, and then this 2 is really 2 factorial. That's really a factorial, but 2 factorial is 2. Then you have x minus a squared. Okay, and if you go on to a cubic, okay, then you end up with this. Okay, this is kind of the structure I want you to see. So when you have a cubic approximation, this is P2. This thing that I circled right there is the quadratic approximation. And then this thing right here goes into the cubic, where you have a third derivative. You have 3 factorial, and you have that power is 3 like that. Now I'll talk about geometrically in this diagram kind of what that's doing, okay? But I'm not going to prove the formula. I'm just going to show you and give you that formula for now, okay? So basically, linear approximation is what you're doing is you're using a first derivative to approximate a function value, okay? That's a slope of a tangent line. If you're doing a quadratic approximation, and let me just kind of stand up and show you what this is doing here. So this is your function, this thing right here in black like that. And what you're doing now is the quadratic would end up being this piece right here. And that's going to be used to approximate that function value. Now notice on this that when you're using the quadratic, the error might be a little smaller on that. And if you go onto a cubic, it might even be smaller still. So theoretically, this different series goes out forever. You go to the next term. The next term on this would just be the fourth derivative over 4 factorial, x minus a to the fourth power, and so forth. So all I want you to see is just the structure of the formula. Okay, that's linear right there. That's quadratic. And then this whole thing right here becomes quadratic. Then you add on the cubic piece and so forth like that. I just want you to see the structure. Does that make sense what I'm saying? Okay. Now we're going to work with this, and once we start doing some examples of what we're going to do, I think it'll make a little bit better sense. But kind of like the problem I did previously, and I'll go right back to where I was. This one where we were doing the square root of 26. Now we did a linear approximation. We could also do a quadratic approximation on that using that formula, but what we would end up doing is going on to the second derivative. And if I did that, you would have a little bit greater accuracy. And we could go to a cubic and so forth. And all we got on linear was we just got, 1 decimal place like that. So we can get a little bit greater accuracy as we go through that. Okay? Okay, so let's go ahead and let's go to page 4. And let's do some examples on this then. Okay. And then I'm going to do one with the square root, and that'll kind of relate to the one that I did with the square root of 26. Okay, so what we're going to do, and this is kind of a good way to start learning, getting a handle on this formula here, and I think this will help you understand geometrically what's going on in that quadratic approximation. So we're going to do these things. First of all, we've got square root of x, a is equal to 4. We're going to approximate 3.9. Okay, so the goal on this problem is to do a linear approximation for 3.9. That's very similar to what we did on the square root of 26. And then we're going to do a quadratic approximation on that. Now, the reason that we have a equals 4 and I took this out of the book, is, well, because you know the square root of 4, right? That's why. So if you're doing an approximation of 3.9, you want to pick a perfect square that 3.9 is close to. You wouldn't want to pick like square root of 100. You want to use 4 because it's only 0.1 away like that. Okay, so to begin with, what we're going to do is we're going to do the linear approximating formula on part A. Okay, so let's start with that part right here, and let's go ahead and write down the formula. So if I want you to do a linear approximation, usually we use P1x. P is standing for a polynomial, and it's linear, so that's really x to the first power. Okay, that's linear. Okay, that formula is f of a, where a is going to be 4. Then what we do is we do the first derivative, and then we do x minus a like that. So if we're going to find the linear approximating formula, that's what we got to do. Okay, and that formula is pretty easy to remember. Okay, so here's what you got to do in this. Well, first of all, we know a is 4, so we're going to have f of 4 plus f prime of 4, and then x minus 4 like that. So what we need to do is we need to go ahead and do the first derivative, and we have to know what f of 4 is and everything. All right, so f of x is equal to the square root of x, so that's going to be x to the 1/2 power. So you want to go ahead and do the derivative of that, first derivative. Okay, so let's see, that's going to be 1/2 x to the negative 1/2, and then I'm going to go ahead and write that as 1 over 2 times square root of x. Okay, so what we're going to do here is actually a very simple thing. So if we do f of 4, well, what's f of 4? F of 4 is just the square root of 4, right? Okay, then we go to f prime of 4. Well, you're going to plug in a 4 there. Okay, so that's going to be 1 over 2 times the square root of 4, and then x minus 4 like that. All right, now let's go ahead and crunch this out and see what we get. So we're going to have 2 here. This is going to be 1 over 2 times 2, so you can do that in your head. So that would be this then. Okay, so this right here is your formula for the linear approximation right there. Okay, and that's kind of stuff that generally, like I said, you do in Calc 1. Everybody follow that okay? Now, it's not that hard to do because you've got a pretty simple derivative. You're just following the formula on there. Now what we're going to do in a little bit here when we get to part C is then we're going to use this formula to approximate the square root of 3.9. And all that means is you're just going to plug in a 3.9 for x, and then that'll give you an approximate value. Okay, so that's linear approximation. Okay, that's step 1. Okay, everybody with me on that? Okay. All right, now let's go to quadratic approximation. Now let's write down the formula. So when we do quadratic approximation, you're going to do this. Now I'm going to write down the formula, but when you're doing this, the formula kind of goes like this. You have f of a, and see, you're going to use the linear approximation like that. That right there is that right there is P1, and we've already got P1. P1 is 2 plus 1/4 x minus 4. Okay, then what you do though is you add on this quadratic term, which goes like this. You say 1 over 2 factorial, then you say second derivative of a, and then x minus a squared like that. Okay, so see, this thing we've already got. We got that from part A. So what we need to work on is we need to work on this part right here. All right? Okay, so what do you need to do basically? You need to do the second derivative. Okay, if we did a cubic approximation, you'd go on to the third derivative and so forth. Okay, so let's go ahead and do the second derivative. Okay, so our first derivative is right here. Okay, so when we do that, we're going to do power rule. So that's going to be 1/2 times negative 1/2 x to the negative 1/2 minus 1. You don't have to write all those steps. That would be negative 1/4 x to the negative 3/2. So that's going to be negative 1 over 4 x to the 3/2, which would be negative 1 over 4, and then you want to write that as square root of x, whole thing cubed like that. So just rewriting the 3/2 power to square root of something to the third. Okay? So that's your second derivative. So what we're going to go ahead and do now is we're going to go ahead and put this together in this formula. Okay, so we need to go ahead and do these two things. Now I'm going to go ahead and just do this piece right here at the side of the paper here, then we'll go back and put this all together here. All right? So let's see. What we have is we're going to have 1 over 2 factorial, which is just 2 times 1. Okay, then when we do f double prime of a, now again, a is 4, we're going to do negative 1 over 4 times the square root of 4 to the third. Then we're going to have x minus 4 to the second. So I'm just doing what this quadratic approximating formula tells me to do. So that's going to be 1/2 negative 1 over 4. And then when you look at this piece right here, just do that in your head. Square root of 4 is 2. 2 to the third is 8. Then we have x minus 4 to the second like that. All right, everybody with me what I'm doing on that? Okay, that shouldn't be that bad to do because it's just second derivative and evaluating. That's stuff you should have good skill on. Multiply this out. That looks like that's negative 1 over 64. X minus 4 to the second. So that is your quadratic term in your series. Okay, this is really a power series is what we're getting then. So what we're going to do now is we're going to put this, just kind of put it all together now. So we already have the answer to this thing right here, right? That answer is P1 of x. So you want to go ahead and write that as 2 plus 1/4 x minus 4. Okay, when you do a quadratic approximation, the linear approximation is built into it. That's the linear term of your polynomial. Okay, now this part right here is going to get replaced with this. Okay, so that's going to be minus 1 over 64 times x minus 4 to the second power like that. Okay, and then that's it. So what I'm going to do is this is our answer to part A, and then this right here will be the answer to part B like that. Okay, so that's a linear, and then that's the quadratic approximating polynomial. You don't need to multiply it out or anything, you just write it in those terms, all right? And then this is the ideal way to do this. One thing I want to say on here is this polynomial, if I say what's it centered at, what do I mean? I mean this thing right here, x minus 4. So it's centered at x equals 4. Okay, like that. Okay, now part C, what we're going to do is, and some of these things I've already done outside of class. I'm not going to do this on the calculator. But what you want to do now is you want to do P1 of 3.9. So remember, what we're doing is we're approximating the square root of 3.9. So what you're going to do is you're going to take this P1 formula in part A, this thing right here, and you're just going to plug in, where you see x, plug in a 3.9. So that's going to be 2 plus 1/4, 3.9 minus 4. Now you could do that on the calculator if you want to. I think I already did that, and I got 1.975. So I just expect you to do that on your calculator. Okay, so that is a linear approximation of the square root of 3.9. That's what that's doing. Okay, then you go on to P2. Okay, well in P2, 3.9, well, you've already got the answer to this part right here. So what you could do here, and I'm going to go ahead and just write it like this. I'm going to go ahead and just do 2 plus 1/4, 3.9 minus 4, like that. Okay, and then I'm going to add in this quadratic term, which is 1 minus 64, and then 3.9 minus 4 to the second. Now this piece right here, we already did, right? So that is really giving you 1.975. That's what we had there. And then when you do the rest of this on the calculator, I'm just going to give you the answer because I think I already did this before class. And you can check my calculation if you want to. I got 1.97484375. So that's the quadratic approximation of 3.9, like that. Okay? So that would be how you take a term, how you can use linear and quadratic approximations for a square root. That would be the idea. Okay? Now, let's go ahead and let's see what the square root of 3.9 is on the calculator then. So, when I do that, let's see, I get 1.975. So notice the linear approximation, we're good to 2 decimals. Then when you look at this quadratic, it looks like we got set 9748, 4. So we're pretty good on this one up to that point right there. Okay, so the idea is the further you go out in the series, what do you think? The more accurate you get. Does that make sense? So, okay, this is we're kind of at the beginning now of what I'm kind of showing you one of the things that series led us to figure out. So if you've ever wondered how in the world does a calculator do the square root of something, well, this is kind of how it does it. Okay, and notice after doing the formula, then just after 2 derivatives, we're already pretty accurate. So if you went out to the cubic and the quartic, you're going to have everything the calculator's got. Okay, that's how that goes. So that's kind of the idea. Whoops. Okay, so do you guys got any questions about what I just did? This is a fairly good thing. Like when we're going to have our test next Wednesday, next Wednesday. That goes, and in chapter 9.1, this would be one thing I'd expect you to do with the calculator. Okay, if you know the formula, that shouldn't be that hard, right? Okay, so that's the idea. And I wouldn't expect you to go beyond quadratic because it's just too much work, but with a calculator, I'd expect you to be able to do something like that. And you can also figure out the error of approximation like we've talked about as well. That's another thing that I usually have you do. All right, is everybody pretty solid with what I did? Okay, that's not a hard problem to do. It's a little abstract to understand, but you'll get to that point. Okay, now we're going to do a few others like that. I'm going to do just one more example to kind of with a trig function, but we're going to basically repeat what we just did with the trig function. So I went ahead and just wrote down the formulas over at the side so we can refer to those as we go through them. Okay, so remember in the formula, this right here is the linear approximating. That's the linear approximation. And then that gives you add that piece on, that gives you the quadratic piece right there. So let's go ahead and let's start by doing the linear approximation. Okay, that's what we want to do first. Okay, all right, so the first thing you need to do in this formula is you need to do the derivative. Okay, so let's go ahead and do f prime of x. Okay, we know the derivative of the cosine is negative sine x, like that. Okay, so then we're going to go ahead and let's put together our formula. So for p1 of x, that's going to be f of a plus f prime of a times x minus a, like that. So that's what we're going to do. All right, now they're giving you pi over 4. We're going to end up approximating 0.24 pi. Why in the world did they give you pi over 4? Because it's real close to 0.24. Isn't pi over 4 really, I mean, it's really 1/4 pi, so that's 0.25 pi, right? So what I typically do is give you this. If you're doing this approximation, you either are going to be given a, or you have to figure it out yourself. Well, what you do, like with trig, is you try to find the nearest value that you know something about from the unit circle. Does that make sense? Okay, that's why I'm using pi over 4. Okay, all right, now when we do this, we're going to do p1 of x. So we're going to do f of pi over 4. Then we're going to do plus f prime of pi over 4. And then we're going to do x minus pi over 4, like that. Okay, now let's just kind of work out the details at the side. So f of pi over 4, the function is the cosine. You were given cosine, so we're going to do cosine pi over 4. Hopefully you guys got that down by now. What's that? Square root of 2 over 2. That's unit circle stuff, so we know that. Okay, let's also do f prime of pi over 4, so that's a part of the formula. So the first derivative was negative sine x. So you want to go through and now do negative sine of pi over 4. What's that answer? And it'd be negative square root of 2 over 2, right? You know the sine of pi over 4 is root 2 over 2. But that negative is going to tack on. Okay, so let's write what we have then. So it looks like what we have is P1 of x equals f prime of 4, which is, or not f prime, f of 4, cosine of pi over 4 is root 2 over 2. Then this would be, and I'm going to write that now as a minus root 2 over 2, and then x minus pi over 4. Now, what I'm going to do on this, and it's okay if you leave it that way, what I do a lot of times on these problems is factor. If you see something that can factor out, you can do that. It's actually okay to give me that answer. That is the linear approximating polynomial. But notice on this, couldn't you just factor a square root of 2 out of 2 out of that? Okay, so let's go ahead and do that. I'm just going to choose to do it on this problem. So if I take that out, I'd have square root of 2 over 2. And then I would have 1 minus x minus pi over 4. Okay, like that. So this will be the answer to part A. That's my linear approximation. All right, everybody follow that okay? Okay, that shouldn't be that bad. And realistically, what you're doing is you're doing y minus y1 equals m times x minus x1. Okay, x1 is pi over 4. The m is the derivative. That's what you did. Yes?
Could you further simplify it to 5 pi over 4 minus x, or does that not?
Oh, yeah, you could do that. I think the reason I'm going to stop at this is just because the structure of the answer, generally we kind of like that center to stay in there, right there.
Oh,
so you can kind of see as you go out in the series, you'd have x minus pi over 4 to the first, to the second, and third like that. So that's why I leave that alone. Okay? All right, so that's part A. Part B, we're now going to go on to the quadratic approximation then. So again, we're doing this whole entire formula right here. We've already got this done. That's done. Okay, this thing is the new thing that we need to do, is that quadratic term right there. Okay, so really what do we need to do? We need to do the second derivative. Okay, so we need to go on to the second derivative of x. Okay, so the first derivative was negative sine x. Okay, so the next derivative would be what? Negative cosine x, right. The negative comes down, that's a constant. And then the derivative of the sine is the cosine like that. Okay? All right, so let's go ahead and let's get this all put together now. So what we're going to do on this P2 now is let's go ahead and just write that down now. So P2 of x is going to be this. Now see, we've already got this right here. Okay, you don't have to do this part again. So you can just write down what I highlighted in blue as square root of 2 over 2 times 1 minus x minus pi over 4. Okay, like that. Now we need to just add in this term right here. Okay, so what we're going to do now is add this on. So we're going to do f prime of a. Well, that's going to be negative cosine. A again is pi over 4. And then really that's a 2 factorial. I just want to stress that because to see, so that you kind of see the pattern on this. And then this would be x minus pi over 4 to the second power right there. So we just need to clean that up and work that out. So again, when you're doing the quadratic, you already got the linear. Then you add that piece like that. Okay, so let's finish this up, kind of clean this up and see what we have. So I'm gonna keep that the way it is because I'm gonna have another square root of 2 over 2 in here when I go to that next term. Okay, so the cosine of pi over 4 is going to be this. Now I'm gonna just sort of write this, some scratch work over the side. That part I highlighted in blue is again square root of 2 over 2. And then 2 factorial is 2 like that. Then you're still gonna have x minus pi over 4 squared like that. Well, this piece right here, what that really is, you can do this in your head, you don't need to write this down. You're dividing that by 2, right? So if you divide by 2, what you're really doing is you're multiplying by a half. So this piece right here is going to give you negative root 2 over 4 now, is what you're going to have. Okay. All right, so if I go on and move on to this next term, actually I'm going to go ahead and just write it like this though. I'm going to just write the cosine of pi over 4 as root 2 over 2. And then that 2 factorial is 1/2. And the reason I'm going to do that is so I can do some more factoring on that. You could write it as negative square root of 2 over 4 if you wanted to. Okay, so does everybody see what I've done on this term right here? Second derivative, evaluated today, 2 factorial x minus pi over 4, like that. Okay, now what I'm going to do on this one, just because I see another common factor, is I'm going to pull that out now. All right, so let's pull that out and do that. You don't have to do that, but if you have a common factor, it's kind of nice to go ahead and pull that out, and then you can kind of see how this begins to work out. So I've got square root of 2 over 2, and then I'm going to have a big bracket. So the first term I'm going to have is this thing. Okay, that thing's going to come down as 1 minus x minus pi over 4, like that. Okay, and then the rest of it is going to be this, this, and this. Okay, after you take that common factor out, you're going to have minus 1/2 x minus pi over 4 to the second, like that. And then that's got kind of a nice structure to it like this. So what I'm wanting you to kind of see on this too is this. We're developing a polynomial. So see, that's a constant, right? What is that? That's x minus pi over 4 to the first. That's your first power. Then that's your second power right there. So that would go on forever in the series. If you continued with the cubic, then you would end up with an x minus pi over 4 to the third, but you would have some other constant there. That would be the idea. Okay, so that would be the formula that we get for the quadratic approximation. All right, that's the answer for part B. All right, everybody with me on that? Okay, does that seem easy enough? Okay, it's not that bad. Okay. All right, so let's go ahead and let's go to part C. Okay, now these things you just kind of do with your calculator. So, and I've already done some of these things. So what we're doing is we're interested in evaluating, we're approximating the cosine of 0.24 pi. Okay, if you read the directions to the problem, it said approximate cosine 0.24 pi. Okay, so what we're going to do, first of all, we're going to do the linear approximation. So that's just going to be plugging in here for x. You're going to have root 2 over 2 times 1 minus, and then I'm going to write that as 0.24 pi minus pi over 4. You would get your calculator out on that, and then you would just crunch that out. Now I'll let you write down what I got, which is 0.72932119591. I don't want to take the time up punching buttons on my calculator, but you guys could easily do that on your calculator, okay? Right? And then that again is the linear approximation. So what that is that's approximately what the cosine of 0.24 pi is. We'll look that up on the calculator in a minute, and we'll see how close we are. Then when we do the quadratic approximation, well, then you just plug it into the second formula right here, okay? So, or you could even just tack on that extra thing like that. So that would be root 2 over 2 times 1 minus 0.24 pi minus pi over 4 minus 1/2 0.24 pi minus pi over 4 squared. You got to be careful when you put that in the calculator. Now what you could do on this is just do this. You've already got the answer to a linear, so you could just tack on this piece, but if you did that, you'd have to remember to multiply that by that constant. So what I got on that on the calculator was 0.72897222527. So that would be approximately what the cosine of 0.24 pi is. And of course, when you do stuff, trig functions on your calculator, a calculator is following some sort of a formula, and it's got some sort of a series formula going behind the scenes is what's going on with that. Okay, that's where that comes from. Okay, so I'm going to put my calculator in radian mode, and let's see how close we are. Which one do you expect would be more precise, the linear approximation or the quadratic one? Quadratic. Okay, so let's take a look. Okay, so we have cosine 0.24. I'll put in the pi like that. Let's see how close we are. So 0.728. Notice that the linear approximation was accurate with the first two decimals, and then the quadratic looked like it was up to 4 decimals like that. Okay, that's the idea. All right, and then another thing I could have you do on that is find the absolute error. If I wanted you to find like the absolute error, what would you do? Like if I said, what's the absolute error between the quadratic approximation and the cosine of 0.24 pi, what would you do? You would just take whatever comes out on your calculator, you would take this value right here, right? And then you would subtract off that value there. And then that would give you how close they are. Okay, that's the idea. That's what the error is. Okay, so that's kind of and that's a good test problem too, to kind of see. I like students to be able to approximate trig functions, square roots, cube roots, stuff like that. Okay, that's the idea. Okay, now what we're going to do next is introduce the idea of a Taylor polynomial, which in a sense I kind of did already. And this is a pretty big deal. Okay, this is Taylor polynomials. Basically, if you look at this, are following the formulas that we just looked at. What we did when we did the quadratic approximation is we did part of the Taylor polynomial formula. Okay, so it goes like this. When you look at a Taylor polynomial, it goes like this. This part right here is the linear approximating formula right there. And it sort of nests its way. Then if you go there, this whole entire thing right there, that's the quadratic approximating. And then what you do is and it's a very cool little formula on here, and to me it's very elegant how this works. When you go out to the cubic, what do you have? You have the third derivative and then 3 factorial, and then x minus a to the third. So what you end up doing is the further out you go, the higher you go with the derivatives, and then the n factorial would always match that derivative right there. Okay, so that would be the idea, is what we get there. And generally what we say is the center is at A. Okay, so again, that right there represents a center at A. All right, and if it was a center at 0, we call it a Maclaurin series, which we'll talk a little bit about today too. A Maclaurin series is a Taylor series, but the center is at 0. And then we'll get to that in just a little bit here. So that's what we mean by the Taylor polynomial. All right. So let's do a little bit of work on this idea here. And what we're going to do on this one is we're going to find, this will be something that you'll be doing with your tests next week too. I might have you do like a Taylor polynomial. I always have you do a Maclaurin series, and we'll get into that a little bit today. And then I'm going to graph this on the calculator. Okay, I don't generally have you do that on a test or anything. The purpose of that is geometrically to help you understand what's going on in the problem. Okay, all right, so what we're going to do is find the nth order Taylor polynomial centered at 0. Now if it's centered at 0, what does that mean to you guys? Have you got that down yet? That would just mean what? X minus 0, right? Okay, that means that A is 0 in this problem. All right, so just for that thing right there, if it says centered at 0, then A is 0. Okay, that's important that you understand that. Okay, then what we're going to do is we're going to do this for, these are usually called the orders of the derivative. Like for instance, if you're doing a Taylor polynomial of third order, then you're going to go all the way out to that derivative and so forth like that. So we're going to start with 0, 1, and 2 like that. Okay, so the first thing we're going to do is we're going to do f of 0. Okay, and we're going to go ahead and work that out. And again, I've given you this exponential function. So f of 0 is going to just be e to the negative 0. So that's equal to 1. Okay, and what that is the constant term of the polynomial. That's what this f of a right here is. In the Taylor polynomial, that's what we just did there. We did f of a. We're centered at a, so we just evaluate the function at that point. Okay, then we go on to the second part, so we need to do f prime of x like this. So I'm going to go ahead and just kind of work on the derivatives. So when we're doing an order of 1, that means it's a linear approximation, so we're doing the first derivative. So let's do the first derivative of this function. So what's the derivative of e to the negative x? Negative e to the negative x like that. And while we're at it, since we are going to go up to the second order, we need to go ahead and just do the second derivative and get it out of the way. So I'm going to go ahead and do that. Okay, so that would be negative e to the negative x. So the second derivative is going to be back to a positive e to the negative x like that. And then we are going to have to evaluate these derivatives too as we go. So I'm going to go ahead and do these things. Okay, from here I'm going to go ahead and do f prime of 0. Again, we're centered at 0. That's a is 0. That's why I'm going to have to do that. So that would just be negative e to the negative 0. So that would be just negative e to the 0 or negative 1. Okay. Then when we do f double prime of 0, okay, well, f double prime is e to the negative x. So that's e to the negative 0. So that's equal to 1 like that. So we kind of got everything that we need when we put this together then. Okay, so when you're doing, if I'm asking you to do a Taylor polynomial of these different orders, it makes sense to just go ahead and get your derivatives out of the way. Just get that stuff done. Okay, so what we're going to do is we're going to actually have 3 answers to this problem. The first answer, what we're going to have is just P0 of x. Okay, and in the Taylor polynomial formula, all that's saying is this part right here. That's f of a. So what was that? That was 1, right? Okay, a is 0, f of 0 is equal to 1. So the answer to that problem is just that. Okay, and one of the things you want to try to do is you want to try to put this together. You want to get the formula memorized. It's not that hard to memorize either, and this is an important formula, so you want to get this memorized. So when we go to P1 of x, okay, then what that is the formula would be f of 0 plus f prime of 0 x minus 0. Again, we're centered at 0. That's where all the zeros are coming from. Okay, so then we just put this together. So f of 0 was 1. Okay, the derivative f prime of 0. Okay, I think when we did that, let's see, we did f prime right here. That was negative 1. So that's going to be plus negative 1 x minus 0. So I'm just going to write that as 1 minus x. Okay, so that would be the answer to P0, the first 0 order, and then that's the first order like that. And that's a polynomial. Of course, it's a linear. You can tell that negative x plus 1 is a line, right? That's a linear function. Okay. Now we want to go to the third order. Okay. And again, you want to get this formula down. So it goes like this. You just sort of build it as you go. You go f of 0 plus f prime of 0x minus 0, which is what we already did. Now, where does the next thing go to? See if you can tell me what that is, if you got that down yet. What do I go to? Second derivative, right? Over what? 2 factorial, right? Okay. Okay, second derivative, second factorial. Then you go x minus 0 like that. Okay, that's how that goes. Okay, and squared, thank you. Yeah, okay. That's a first power, then second power like that. Okay? So now when we put this together, it kind of goes like this. Well, this whole thing right here we already did. Now, if you can go ahead and put it together if you want to, I'm going to just do this and put this together. F of 0, that was 1, like that. Okay, and then when we did this next thing, this would be plus, the first derivative was negative 1. You got to kind of keep track of stuff. Then x minus 0 to the first. Okay, f double prime of 0 was 1. So that's going to be, this part right here is going to be 1. 2 factorial, of course, is just 2 times 1. Then we have x minus 0 to the second. Okay, like that. So you kind of build that as we go. So if we wrote that out now, we would have 1. this whole thing right here would be minus x. And then this part right here would be plus 1/2. Then you can write that as x squared. And that's a quadratic, so that would be the answer to the second order of the Taylor polynomial like that. Okay, that's the idea. Okay, does that make sense what it did? Okay, now you're following a formula, and most of what you're doing is arithmetic, and you're doing a derivative, so it's not that hard of a thing to do. Now, one of the things I wanted to show you on this then is this. I don't think I put a graph on your handout. I don't think I did anyway. Did I, or I did not? Okay. Now, I want you to just sort of pay attention to this. You don't have to necessarily sketch this out. But what you would be doing on this is basically this. I'm going to go ahead and do this to show you what I did on my calculator. So if you want to do this along with me, you can. I would expect you to do this with a calculator. I'm not expecting you to do this any other way with this type of a problem. So what we're going to do is we're going to put in e to the negative x. Okay, that's the function that we're approximating. And then if I went through and did like the 1 minus x, that would be the linear approximation. So I'm going to put that in. Then the quadratic approximation is 1 minus x. So it has that part built into it. Then it would be plus 0.5x squared like that. And then we're centered around 0. So the problem was centered at 0. So I think probably what I'm going to do on this is just maybe go from -2 to 2, because the center is somewhere between -2 and 2. Scale by 1, and as far as the y-axis, maybe go up to 3 or something like that. Okay, so I'm going to try something just kind of like this. And the graph that I have on here already doesn't have the line in it, so if I do that, what's going to come out, that's the e to the negative x in blue, that's the linear approximation, that's the quadratic approximation. Well, obviously, which one looks the most like the function? The quadratic, okay? It approximates that curve. Now, it starts kind of messing up when you get out here, but when you're at that center right in there, it's pretty accurate. So the idea is, if you went out to a cubic, if you did a cubic approximation, it would approximate that curve even closer. So what I'm trying to show you with this is that this thing right here is what we're trying to approximate. If you look right there, it's almost indistinguishable. If you're like within maybe a half and negative a half, you can hardly tell the difference, right? So they look almost the same. So what you're doing is you're taking an exponential function, and we're approximating it by a polynomial. All right, does that make sense? Okay, that's the idea. Okay, so that's what Taylor polynomials are doing, and they're allowing us to approximate values on this thing. And we usually call this kind of function, maybe you've heard this before, we call that a transcendental function. And transcendental functions can be represented by polynomials, but they don't have like add, subtract, multiply, and divide. Another example of transcendental would be a trig function like that. So that would be the idea. Okay. All right. Any questions on that with anybody? Okay. Is this interesting? It kind of is. Okay. At least kind of gives you an idea of the mathematics behind approximation on some of these types of transcendental functions. Okay, so I think I'm going to do like one other illustration of that. Then we'll get a little bit into the errors and that kind of thing, and remainders and that kind of thing. Okay, so let's see. Let's look at this. Just kind of repeat the same thing with this one. We're going to find the nth order Taylor polynomials. We're just going to do the first up to the second derivative. Like on a test, I don't generally go further than a second derivative unless the derivative is super, super easy. I do that sometimes on a Maclaurin series. So, and a Maclaurin series just means the center is 0. Okay, so this one right here is we're centered at 0. So again, that tells you A is 0. Okay, and we're going to do the same kind of thing on this. So what you really want to do with this is, since A is 0, because the center is 0, you want to go ahead and do these things. You want to do, let's see, f of x is 1 plus x to the negative 1/2. It makes a lot of sense on these problems to just go ahead and do your derivatives and get that out of the way. And then evaluate your derivatives at 0, okay? So let's go ahead and get all of our derivatives put together, okay? So the first derivative would be, by chain rule, that would be negative 1/2, 1 plus x, okay? If you subtract 1 from that, you're going to get negative 3/2, okay? The derivative of what's inside is 1, so we would have that then, okay? And let's see, if we do that, that would be, I'm going to go ahead and just write this as negative 1 over 2, 1 plus x to the 3/2 power. And that'll be good enough for what we're going to do. Okay, then let's go on, let's go to the second derivative. Okay, so we're working with the first derivative is in a non-simplified form is like that. So let's take the second derivative. So that's going to be negative 1/2 times negative 3/2. 1 plus x, subtract 2/2 from that, you get negative 5/2. So that looks like that's going to be 3/4. And I'm going to go ahead and write that as 1 plus x to the 5/2 power like that. Okay, so now what we've got is we've got our first derivative and we got the second derivative. Okay, now the Taylor polynomial formula essentially is going to tell you you need to do these things. You need to do f of a, f prime of a, and f double prime of a. So we need to go ahead and just do this. Generally, if I'm doing Taylor polynomials, that's what I do is I just start going out and working those things out at the beginning. Okay, we're going to get 3 answers to the problem. The first thing we're going to do is P0 of x. And again, that is just telling you the order that you're working with. So we're not doing a derivative yet. What we're doing on this is we're just taking the function, which I gave you, and you're going to evaluate that at 0. Okay, so when we do that, we're going to have 1 plus 0 to the negative 1/2. So that's going to be just 1 to the negative 1/2. So that's going to be equal to 1, okay? That's really just 1 over 1 to the 1/2, so that's equal to 1. Okay, you can do that in your head. Okay, so we have that. So what we get is, therefore, that means P0 of x is equal to 1. That's the first answer of the problem. That's the 0 order. Okay, now what we do is when we go to the second order, or the first order, when we have the first derivative, then we're looking at this piece of the Taylor polynomial, which is a linear approximation. Okay, like that. Calc 1 stuff, really. Okay, so when we do this, we're going to have P1 of x, so we just follow this formula precisely here. So that's going to just be f of 0. Okay, then it's going to be plus f prime of 0. Then it's centered at 0, so it's x minus 0 like that. Okay, we just plug in what we have. So it looks like f of 0, let's see, f of 0 was 1. We already did that. Okay, f prime, we haven't done f prime of 0 yet, so we need to go ahead and just do that. Okay, so if you do this, here's your first derivative. So I'm going to take this first derivative and I'm going to plug in a 0. So that's going to be negative 1 over 2, 1 plus 0 to the 3/2. Then x minus 0, of course, could just be written as x like that. Okay? Well, just crunch out the details. I'm not going to give you anything real crazy on the arithmetic here. So anyway, what is this? What is 1 to the 3/2? 1 to any finite power is 1, right? So do that in your head. This thing right here is just going to be negative 1 over 2 times 1 to the 3/2. So that's just going to be negative 1/2. Okay, so I'm going to write this as minus 1/2 x. Okay, so that's what the answer to the first order Taylor polynomial is. And that's a linear approximation. That's a linear equation, correct? Okay, everybody with me on that? Okay. All right, now what we need to do is we need to go on to the third Taylor polynomial. So we're going to go to the second order. So we do P2 of x, standing for the second order polynomial. And then this goes like this, okay? We're going to have, when we put this together now, you want to do this. And if you look at this formula, now we're doing this whole thing right there. So we've already got the answer to the linear. So I would just write down the answer to the linear. That's 1 minus 1/2 x like that. Okay, that's what that piece right there is. Now just tack on this quadratic term, which is going to be f double prime of 0 over 2 factorial, then x minus 0 squared like that. Okay, so all we got to do is just work with evaluating that derivative, and then we should have our answer to our problem once we do the arithmetic. Okay, so I'm going to write this down as 1 minus 1/2 x. Okay, let's see, our second derivative is here, so we're going to plug a 0 in for that. So that's going to just be, and I'm going to write this as 1 over 2 factorial. Then when I do f double prime of 0, you can do this in your head if you want to, that's 3 over 4, 1 plus 0 to the 5/2, then x minus 0 squared like that. Okay? And let's see what we get on this then. Okay? Well, this thing right here is going to be 3/4, because this thing right here is just going to be 1. If you can do something in your head, do that in your head. Everybody with me on that? Okay, that's just 1 to the 5/2, so that's 1. So what you end up having is 2 factorial is 2. So you really have 1 over 2 is the 1/2 part times 3/4. So that right there is going to be 3/8. That's what that coefficient is going to be. So our final answer for the second order Taylor polynomial is going to be 1 minus 1/2 x plus 3/8 is what this whole thing right there is, and then that's x to the second. Okay, so that is your second order Taylor polynomial like that. Okay, you guys see how everything is nested within. That's kind of the important thing. I think we've done enough of that by now. You hopefully can see that. So see the 1, it's there. See the 1 minus 1/2 x, it's there. Then you have the quadratic term. If you went to cubic, then this would be a part of the answer, wouldn't it? Then you would just add in third derivative. It would go like this. Third derivative over 3 factorial x minus a to the third and so forth. Okay? That's the idea. Everybody okay? Okay. Okay. So that's kind of what I wanted to show you on that. I think I'm going to go ahead. Next thing I want to look at with this is just doing some things with some error. Now this one you don't have to do too much calculation on. This is just a problem that I took out of the book here. So you'll see some similar things on your homework. Okay, so what you're doing with this one is, now this one you're not doing the Taylor polynomial. They actually gave you the Taylor polynomial on this one. So what they're saying is use the given Taylor polynomial for P2, that's a quadratic approximation, to approximate the given quantity. So what they've done is we're going to approximate this. That's the function. We're doing a cube root. That's cube root of 1 plus x. And then what they've done is they've went ahead and did the Taylor polynomial for you. So we're going to do that, and then we're going to compute an absolute error. We hadn't done an error yet, but we've learned how to do that. So basically what you do, and you can do this in your head, by the way, guys. You know, I'm going to go ahead and do it this way. So you need to kind of figure out what is A? Okay, what's the value of A? There's two ways to do this. One way is to do it in your head. The other way is to do like this. You could take this cubic function, 1 plus x, and you could set it equal to this. Okay, like that. We're going to find what x is, and that's going to give us the value of A like this. Well, I think you can do this in your head of what would x have to be? It'd have to be 0.1, right? Okay, 1 plus 0.1 is going to be that. And yeah, if you can do something in your head, then by all means, just do it in your head. If you don't see it, I'm going to go ahead and do it this way because there might be times when you can't see that. So actually the way you would solve this equation would just be to cube both sides like that to get rid of the cube root. And of course that would give 1 plus x. this would be 1.1. Then if you subtract 1 from both sides, you would get x is equal to 0.1. So what we're going to use is we're going to use we're going to center this polynomial at 0.1, not 1.1. Okay, like that. Okay, so we have that. All right, so what you're going to end up doing with this one then is they've already given you the quadratic approximation, so you're going to do P2 of 0.1. Now it's important on this one that you don't use 1.1. That is a mistake I think a student would make if you're not paying attention, because this Taylor polynomial was based on this function. Okay, so the idea is you need to know what x is, so don't use 1.1, use 0.1. And then you just plug into the polynomial they already gave you. So that would be 1 plus 0.1 over 3 minus, and then that would be 0.1 squared over 9. I like that. And then you just do this on the calculator. And I've already done this, so let me see if I wrote that down. So just to save time, if you did that on your calculator, you would have 1.03, then you'd have a whole bunch of 2's. I think I just wrote whatever came out on the calculator. 1, 2, 3, 4, 5, 6, 7, 8. Okay, is what I did. I just took whatever I got on my calculator all the way to the end. Okay, so that would be what you have on part A. All right, now I'm going to get my calculator out, and what I'm going to do here is I'm going to look at what the cube root of 1.1 is then. So that's what we're approximating. So on a TI, if you go math, and then you have cube root is under option 4, so I'm going to put in cube root of 1.1, and we're going to compare it to this value right here. Okay, so I'm just going to go ahead and write that down. So the cube root on 1.1 on the calculator, 1.032280115, like that. Okay, so this would be the answer to part A. Would be that's what the Taylor polynomial approximates that at. And then part B, we're going to go ahead and find the error. Okay, so what do you do on the absolute error? You just subtract the two. It doesn't matter what order you subtract them in too, because you generally have the absolute value anyway. So we usually say like f of x, and then we usually say like the P2 of x. Now we're approximating that at 0.1, so I probably should write that as f of 0.1 minus the Taylor approximating, the quadratic approximation, like that. Okay, and then just subtract the 2. So you would just take this is the one that I got on the calculator, 1.032280115, and then the approximation, okay, like that, and then that would give you that value. Okay, now let's see, when I did this, I think I got some scientific notation. I think if you put this on the calculator, I think you're going to get 5.79 times 10 to the negative 5. You can check me on that if you want to. Hopefully I did that right. Okay, so that's pretty accurate. So the idea is, you know, in scientific notation, this is just moving the decimal to the left 5 places. So that's what you get. So that's approximately what your error is. So that's a tiny error, isn't it? Just by going out to a second order in the Taylor polynomial, you get pretty accurate. That's the idea. Okay? Okay, does that make sense? Okay? All right. This is not the hardest part of the section. The hardest part of this section is probably the stuff with remainders in the Taylor polynomial. So I'm going to do one more thing here, and then we'll go ahead and do a break here. I think this is pretty similar idea with the Taylor polynomial then. Okay, let me do one that's got a trig function. And generally on these problems, we're looking at things where the derivatives are fairly simple. Okay, so we're going to do one more round of the Taylor polynomials on here. And then this time with a cosine. This time we're going to be centered at pi over 6. That's what the value of a is. So what does that mean? It means in the Taylor polynomial, what are you going to have? X minus pi over 6, right? To the first, x minus pi over 6 to the second, and so forth. Okay, that's the idea. Okay, so let's go ahead and just do these things. We have f of x is equal to cosine x. So a good way to start off these problems is just to go ahead and start this way, and then go ahead and do f of pi over 6. Just get all this out of the way before you start putting in building your Taylor polynomial. Okay, let's see. The cosine of pi over 6 is, let's see, on the unit circle, pi over 6 is 30 degrees. So that point on the unit circle is square root of 3 over 2, 1/2. Okay, I always remember it's out as far as possible. That's why square root of 3 over 2 is x. It's up as small as possible. That's why it's 1/2. That's how I remember that. Okay, so what's the cosine of pi over 6? Square root of 3 over 2. Okay, so that's an important piece of information that we need in the problem. Okay, then we want to go on to the first derivative. Okay, first derivative of cosine is what? Negative sine of x. Okay, like that. And while we're at it, we need to go ahead and just do f prime of pi over 6. So that's going to be negative sine of pi over 6. So what's that? Y value on a unit circle, right? So that should be negative pi over 6. Okay, like that. Okay? And then since we are going to the second order in the Taylor polynomial, we need to go ahead and do the second derivative like that then. Okay? All right, everybody good so far? Okay, what's the second derivative then? That's going to be negative cosine. The negative comes down. The derivative of the sine is the cosine. So we got that. Then we're going to go ahead and do second derivative, pi over 6. Yes?
You said the negative sine of pi over 6 is not negative pi over 6.
Yeah. That's the one.
Oh, negative 1/2. Okay. I even put a check mark by it. Pi 1/2. Okay. Thank you. All right, so let's get that corrected. Okay, so we have negative 1/2. I'm sure I would have caught that later. Okay, now let's go to this. So f double prime of pi over 6 would be negative cosine of pi over 6. So what's that? Okay, negative square root of 3 over 2. Okay, yeah, there's your cosine. There's your sine. Okay, so that would be negative square root of 3 over 2 like that. So I've kind of crunched out the derivatives. Now I'm ready to just put this all together. So this is a good way to start the problem. So we're going to go ahead and do these things then. So P0 of x, we're going to go ahead and do that first. And then we'll move on to the first order and second order like that. Okay, so, right, when we do this, you're just doing this piece right here. That's P0 is that constant term right there. So that is f of pi over 6. So that's equal to square root of 3 over 2. Okay, so we would end up with the result. P0 of x, that's the constant term in the Taylor polynomial, is going to be square root of 3 over 2 like that. Okay, that's the idea. Okay, now we move on to the first order. Okay, when you do the first order, now you're looking at this whole entire thing right there. Okay, so what you do is you do this then. Okay, now that's going to be f of pi over 6, which we already have. Then it's going to be plus f prime of pi over 6. Then it's going to be x minus pi over 6. That's to the first power. So just to emphasize that like that. Okay? All right, so when we put this together, let's see what we got. We got P1 of x is now going to be equal to f of pi over 6 is square root of 3 over 2. Let's see, f prime of pi over 6 was negative 1/2. So this term here is going to be minus 1/2. And then x minus pi over 6 like that. Okay, so that should be the answer to the first order Taylor polynomial like that. Okay, everybody with me there? Okay, now let's move on to this last order here. Okay. All right, so I think I got everything right there. Okay, so let's see. Now we go to the P2 of x. Okay, and then this is going to be this whole thing now. Okay, again, you're just kind of building it as you go. Okay, so what we have is f of a is square root of 3 over 2. f prime of a, x minus a, we already got. That's minus 1/2 x minus pi over 6. Okay, now we need to fill in this piece right here. We move on to this. So what we go ahead and do is we do plus f double prime of a. I'm going to go ahead and write this down. So that's f prime of pi over 6 over 2 factorial, then x minus pi over 6 to the second power like that. Okay, so let's put that together and then we're done. So let's see. Let's do this piece kind of at the side here. So let's see. If you have f prime of pi over 6 times 1 over 2 factorial, let's see, f double prime was negative root 3 over 2, so that's negative root 3 over 2. 2 factorial, of course, is 2, so that looks like that coefficient is negative root 3 over 4. I like that. Now we're ready to write our answer. So we're going to get P2 of x is equal to square root of 3 over 2 minus 1/2 x minus pi over 6. Okay, this whole thing right here we just crunched out was negative root 3 over 4. So I'm going to put this as a minus now. Root 3 over 4, and then we have x minus pi over 6 to the second. Okay, and then that is your second order Taylor polynomial like that. Okay, now what I did on this, I'm not going to take the time to do this on my calculator. It takes time to punch all these buttons in. But this diagram, I just want to show you kind of what's going on this, is what we were doing in this problem was we were doing the, let's see, what was the problem? Cosine of x. So cosine of x is really this thing that's in black right there. Okay, now I'm only doing this since we're centering this around pi over 6. I think the way I did this was this is pi over 6 right here. This is pi over 4, and then this is probably pi over 3. That's probably the way I scaled that. I probably took that up to pi over 2 or something. And what this one is this one is the linear approximation. Okay. This one right here, the one that's in this color, I think is the, hold on, I think that's wrong. I think this is probably the cosine right there. Is that one is. Cosine of x, I think this one in black is the quadratic right there. So you're going to have like a linear approximation, which is this one. This is the constant right there. Okay, so that is the square root of 3 over 2. And then this one in black is the linear approximation formula, which is this. And then this one right here is the quadratic, which is this. So what I'm trying to show you on this is the one that most closely approximates this quadratic, this cosine curve, is that quadratic. Okay, now it starts losing some accuracy, but then if you went on to a cubic, you would probably have something a little bit closer. Okay, does that make sense? Okay, so graphically, you can kind of get a good understanding of what you're trying to do with these polynomials. All right, we got any questions about any of this so far? So it's like something you can do okay? Absolutely. Okay, it's not that bad.